Hi there, it's Dr. Peterson, and I'm going to show you how you can use the chi-square statistic to perform weighted least squares fits in your experiments to match your models to your data, and also how you can use spreadsheet functions to calculate the chi-square probability and thus perform the chi-square test for goodness of fit. This is the chi-square formula. Now, because we are dividing by the standard deviation or uncertainty, that means that data points that are more uncertain will have less weight in the overall sum. Here we have some clearly made up data. In this column, I have a simple linear model whose parameters are in these two cells. And in this column, I'm taking the square difference between the data and the model and dividing by the square of the uncertainty, which is effectively the terms in the chi-square formula we just looked at. In this cell, I'm summing all of the weighted square error terms, effectively calculating the chi-square. To fit the model to my data, I adjust the parameters in the model in a way that reduces the chi-square. I can do this automatically using the solver in LibreOffice Calc. Be sure to watch my video on installing and using the solver if you have questions about that. Earlier I said this was a weighted least squares fit, but all these data points have the same uncertainty, so the weights are equal. But if we took a different data set and say this point had a very large uncertainty, and now we use the solver to minimize the chi-square again, we can see that that data point has much less weight on the overall fit. And our chi-square is also lower because that one data point doesn't have as much weight in the overall sum. Once we think we have the best fit of our model to our data, we want to be able to actually say if it's a good fit. Is the data actually being governed by our model? As a first step toward that, we can calculate the reduced chi-square. First, we need the number of degrees of freedom. That's simply the number of data points we have, in this case 5, minus the number of constraints in our model equation. In this case, we just have 2, the slope and intercept. Then we just divide the chi-square by the number of degrees of freedom to get the reduced chi-square. If the data is governed by our model, then we expect that any deviations in the individual measurements should be roughly on the order of 1 standard deviation, and so the reduced chi-square should be close to 1. However, we'd like to be able to say something a little more concrete and quantitative than just our reduced chi-square is close to 1. And for that, we will use the chi-square probability test for goodness of fit. These are plots of the chi-square distribution or probability for several different degrees of freedom. In order to understand what the chi-square test is, I think it's more helpful to think of it as a test for badness of fit. In science, we don't claim to be able to prove things are true, only that we can eliminate certain untrue possibilities. With the chi-square test, we're asking, what is the probability if I redid this experiment many times that I would get a larger reduced chi-square than what I did get? And if that probability is under a certain very low threshold, then it's very unlikely that my data is governed by the model I've chosen, and I can reject it. We often use a threshold of 5% or maybe even 1%, but you always state what your threshold is for rejecting the model. To actually calculate this probability, we need to integrate the chi-square distribution from our reduced chi-square value up to infinity. This is difficult to do by hand, so many people often look up the value in tables in the appendices of statistics books. However, you can use spreadsheet functions to calculate it for yourself. The spreadsheet function we're going to use, which is the same in LibreOffice Calc, Microsoft Excel, and Google Sheets, is chi-square.dist.rt, which gives the right tail probability of the chi-square distribution. It takes as its first argument the chi-square value, not the reduced chi-square, mind you, and the second argument is the number of degrees of freedom. What this tells us is that there's a 32% probability that if we redid this experiment many times, we would get a larger reduced chi-square than the one we got with our data. So we have no reason to reject that this model governs our data set. If we go back to our original data set with equal uncertainties, and then use the solver to minimize the chi-square and get the best fit, we see that our chi-square probability is less than 0.02%. This means that at the 1% significance level, we can reject that this data is described by our model.